Alright, so in this video we're going to look at h of x when it equals f of x, which is a sine bx plus c again, and a cosine bx plus c, which is g of x. These two functions multiplied together. So we're going to look at what this is right here, h of x, which is if two functions multiplied together, and we are going to look at, first I'll just put the graphs of a sine bx plus c and a cosine bx plus c up here just to compare the graph of h of x, a f of x time multiplied by g of x, and see what kind of relationship we see between the two graphs of sine and cosine and the graph of the two functions multiplied together. So as we can see, the graph of h of x is in black, and it has a smaller amplitude than either than sine or the cosine graph. It looks like it's almost half of that value, and it looks like the periods are staying the same, and the peak of this graph, like where the amplitude is its highest right here, the amplitude, it looks like it lies between the two graphs of sine and cosine. Again, just the way that our previous h of x, f of x plus g of x did, but the amplitude of f of x plus g of x was higher than the amplitude of f of x multiplied by g of x. So those are some initial observations that I'm making in this graph. So now I'm going to take the graphs of f of x and g of x off and just see what happens when we change the values of a, b, and c, and vary them, and I just want to see what happens to the graph of h of x right here. So I'll start by increasing a, okay. So increasing a, we can see the amplitude is definitely getting bigger. I just want to see what what f of x, a sine bx plus c looks like with a increasing compared to h of x. So it looks like the amplitude of h of x is smaller than the amplitude of sine bx plus c when up until a is about 1.6, maybe like close to 1 point. When a equals 2, the amplitudes are equal, and then the amplitude of h of x seems to be increasing at a faster rate than the amplitude of sine x. And as we observed before, these values, they seem to be operating on the absolute value. The amplitude seems to be the absolute value of the value of a. So going to negative numbers doesn't necessarily do anything for us, except it just, once we're at 0, let's see what happens when we're at 0. When we're at 0, we have just the x-axis as our graph, and then we just have the absolute value of the number, the a value, that's changing the amplitude of h of x. Okay, so let's take this graph back out. Let's see what happens when we're changing the value of b for this. So it seems to be doing kind of a similar thing to what we talked about when we were looking at f of x plus g of x. So since the period is 2 pi divided by b, and the smaller that b is, the bigger the number that we're going to get when we divide 2 pi by a small number. So that number is big when we have a small number, but 2 pi over b is small whenever as our number gets bigger. So the width of the period is getting smaller. So we're getting more. We're getting more of these iterations in one one measure of 2 pi. So there's that. And let's see what happens when we change c. When we increase c, so when we move it to the positive side, from 0 we move it to the increasingly positive numbers, it seems to be shifting the graph of h of x to the left, and then I predict that it's just going to do the same thing whenever we, it's going to do the opposite whenever we switch to negatives. It's going to move to the right, and this is happening because of what we talked about before. Yes, so a number being added or subtracted from the x, the input of a function, it's just going to shift the graph horizontally, and if it's a negative number, it's going to move it towards the positive side, which is towards the right, and if it's a positive number, it's moving it towards the left. So those are some of my initial thoughts on this.